Polymers.
Okay, so today we'll look at chapter 10. We look at ceramic first, then we go into polymer and composite. So CL3 will be your test 2, question 1. CL4 will be test 2, question 2. Okay. Alright. So basically, we already cover for most of your final exam question. CL1 question 1, CL2 question 2, CL3 question 3, 3 compulsory question already covered. So now we go into the question 4, question 5 for CL4. Okay. So your assignment, again, your assignment due, put maybe last week, week 14. No, I need 1 week, maybe week 13. I need 1 week to marks. Huh?
What's the assignment?
Assignment, you go into Canvas. There's assignment, you go there, submit. There, I think there's a 10 question or 20 question. You need to submit. Okay. So either you submit or don't submit. You didn't submit, 0 marks here. Okay. So lab report, again, I push it to the last week, week 13. Right. This one. Okay. No, your lab report have to submit a bit early. Your lab report week 12. Okay. Now we look at this chapter 10. There are a few section, polymer and ceramic. So we go into ceramic first, because we'll look at a few phase diagram for ceramic. Okay, now what is ceramic? Ceramic is inorganic, non-metallic material. Okay, they are inorganic, non-metallic materials. So they are consist of metal, non-metals, and then they have ionic and covalent bonds. Okay. So they are used for traditional ceramic material, like what you see on the screen here, clay, bricks, tile. These are the traditional ceramic materials. And structural ceramic material is those modern tools. Example, if you ride an aircraft, it's more on the engine parts, right? And your sport car also, most of sport car engines parts, they're made of ceramic part. Okay, properties of ceramic materials. You know that ceramic, typical one, traditional one, they are hard and tough. They are hard and easy to break. However, for structural materials, they are hard. They are very strong compared to conventional ceramic. However, ductility of the material still remain their weakness, means they're easy to break at a certain direction. Both ceramic material, either a traditional or a new one, they are good in their electrical and thermal insulator. Okay, so they can only work as electrical at a certain condition. And thermal, normally they work as an insulator, right? And because they have a high melting temperature and stable chemically, that makes them become an insulator. These are the thing, ceramic. So this table will tell you some of the ceramic compound. All this carbide, oxide, diocide, dioxide, nitrate. So they are the ceramic compound. Okay. So their bonding, electronegativity difference, percentage of ionic, covalent characteristics, and so on. So these are the two things that is important for ceramic: percentage of ionic character, and covalent character. Okay. So again, for packing ions, they are influenced by two: ion reference size and also electrostatic charge. These two will tell you how they pack the ion inside ceramic. So relative size of ion and also electrostatic charges. These two. Okay. So we recap what is coordinate number. You learn about coordinate number in the early chapter, right? So, for example, the one that you see over here, there are some stable and unstable states. So this is stable, where the size fit very nicely in between the molecule or between the sphere. This one also stable. There's less of gap that it can allow it to move. This one is unstable, where the size is less than 15%, and also the size is very, very small. Okay, the rest you reach. So when you talk about ceramic, you have to mention ions. Okay. So when you talk about ion, you talk about radius ratio. Radius ratio, we talk about two types of ion only: positive charge, negative charge. Positive charge we name it as cation. Negative charge is anion. So positive and negative, you take the ratio, radius, the radius, then you get the ratio. Okay. Then there's one term called critical radius ratio, which is ratio the anion just touch each one another and contact the center of cation. So means the okay. So means this one, the critical radius ratio is important for ceramic chapter, because when you with this minimum or critical radius ratio, you know that whether it's stable or not stable. And also from this number, you know that the CN number, coordination number. So this table, we expect you to memorize. Like you memorize G equal to 9.81, right? So when you do your calculation, you get your R positive divided by R negative ratio. When it is reach a certain number, for example, when it reach 0.7 and above, the CN number is 8. Means along the charges, you have 8 electron, 8 sphere, it touch. So when the numbers R positive divided by R negative is more than 0.4, CN number is 6, meaning it touch 6 sphere around the negative charge. Then this one also. This one apply the same. If the number is 0.2, then it's 4. More than 0.15 is 3. So of course in tests you won't get very close to this number. For example, if you take R positive and R negative, and your calculation, you come out with 0.512. What is the CN number? 6. If you get ratio R positive divided by R negative, you get 0.5 is less than this number. So the number is 6, no 7. It's either 3, 4, 6, or 8. No 7. Okay. So it's either more or less. So if you let's say this one, if you get less than 2 but more than 1.5, 1.15, then it's 3 lor. Okay. Okay, so important is that you remember these 4 magic number. It will not be given in the test. We assume you memorize as the gravity force, 9.81. But this is all the magic number for ceramic table, ceramic chapter. So this is another illustration how they pack together. If the number is less than 0.155, it pack like this. So means the ion and cation, it contact with 2. The negative charge contact with 2. If it's 1.55 to 2.25, then it's 3 like this one. It touch 3 sphere. Then 4 sphere, small sphere like 3 at the bottom, 1 at the top. Okay, 3 at the bottom, total 4. It touch 4 sphere. So 3 as a base, 1 at the top. Okay, then this one 6. 6 is the base is 4. The base is 4 sphere, 1 at the top, 1 at the bottom. Total 6. Then this one 8. 8 is 4 top, 4 below. 8 at the center. Okay, so this one important is the number it's a number. So this table try to remember these 4 numbers. Okay, 4 number 0.73, 0.41, 0.22, 0.15. Okay, less than this number is 2. Okay, now from this exercise, calculate the critical radius ratio R over capital R for triangular coordinate Cn equal 3 of 3 ions of radius R surrounding a central cation of radius R in the ionic sonic. So you want to find the critical minimum radius for this one. So this is the steps that we expect you to prove that the Cn at a certain number. Okay, so this one is show you how to do Cn3. So in the test, you need to go home and think how you prove Cn5, Cn6, Cn8, no 5 lah. 2, 3, 4, 2, 3, 4, 6, 8. How do you prove all these number? So I show you 3 first. Okay. Now, if you want to find 3, so you draw 3 sphere and then hidden in the center. Middle is the middle is the cation, positive charge. Cation, cat ion, cat ion. Right. So so when you draw this one diagram and then you label center, 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 ABC, then this one is your E. Then you can start to draw triangular, and this one also got a small right-angled triangular. Okay, right-angled 90 degree here. B here. Okay, then you prove what is the cation ratio there. So 3 anion and cat ion with radius. Okay, large ion is capital R, small ion is a small r. Okay, so if you have a triangular ABC with the same r, this one is small r. So but this side AC, BC, and 3B AB is the same. So all the angle here is 60. Right? So D, this DAE is 30 degree because here is 60. 60, half of it is 30. So then you enlarge the triangular. So you have 30. Then here to here is capital R. Capital R is large sphere. Large sphere. This is onion. dash R, right? So now because this one is sorry, this one is so large R, and then this one is a large R plus a small r. So large R plus small r, so total capital R plus small r. Okay. Then this is the 90-degree. So AD is big R plus small r. Cos 30, cos is this one, divide by this one, side hypotenuse. So cos 30 is 0.88, 0.866. AE is R. This one is AD is R plus small r. Then your big R is this one. Big R equal to 0.866 bracket R plus R. Okay. Then you take the ratio. Okay. You take the ratio. This one multiply this one, multiply this one. Collect the R together. All right. Then your small r divided by big R is 0.15. Small r is middle one. Okay. So this is how you prove lah. So when this ratio is 0.15, 155, so you refer to the table or this one based on this table. So 155 ma. Okay. Remember the symbol here. The symbol here is equal, equal, equal. So when it's 155, then it's 3 less than this number, then it becomes 2. Okay. 3 decimal place, 3 decimal place. Okay. Okay, now predict the coordinate number if you're given the radius of this one, and this one. You have 3 charges, positive charge and negative charge. All right. So find coordinate number for CSCL. Now you need to guess. You need to memorize the 4 magic number. Then you do the ratio 4. Only lah. Yeah lah. 4 number. 155, 0.25, 0.41, and 0.73. To have less than this number. Less than 0.15 is 2. Okay. I can't, this one, less than 0.15. Okay. Okay, so you combine the number. Okay, so this one, CSCL, CS plus CL. So you take Cation anion. Okay, press your calculator, you get a number. 0.94. 0.94 is what? Okay, so it's more than 0.7 is 8. Okay, so you do the same for the second one, also same. NaCl, you press calculator, you get a number. So 0.56 is within here, but it's more than 0.41 is 6. So this is a very easy to score number. This is a very easy to score kind of question for test 2. Okay, only need to memorize these 4 numbers. Then you do the ratio, then you tell me what is the coordinate number. Okay. Don't only don't mess up lah. The Cation and anion lah. Don't catch up. Don't. Okay. Now next is on the processing of ceramic, how you process ceramic. So there are 3 steps: material, forming or casting, then you do treatment or heat treatment. Okay, so these are 4. So preparation, powder, you shape the wet clay, drying, then you do firing. Okay. So here, when you do prepare the powder, you have a loose powder with the air. Then when you do wet clay already, it's very near, the particles very near. Then when you dry, you pack already together. Then you fire it, they kind of glue together. Okay. So when you do heat treatment or thermal treatment, there are some chemistry happening inside. Okay, material preparation, this one you read lah. So material preparation is you break down the raw ingredient. Yeah. So for ceramic, you only need water. Ceramic, you only need water to bind them together. For advanced ceramic material, you add in chemicals, or we call it additive. Okay. So forming, there are 2. Forming, you have dry forming, plastic forming, and so on. So cold forming, you use a die and do so, right? So in the early chapter also, we introduce you what is forming, what is casting, what is extrusion, and so on. So pressing is another one. You have a die there, then you press, get a shape. So this process is for maybe for the light bulb, the light bulb, the holder for the light filament and all this. Is a forming. Okay. So you fill the die, you press it, and then you send it into the furnace to dry. Okay, so another one is called isostatic pressing. Iso means same, static means same forces or same pressure. So it's put inside there. It's a pin, and then you put inside the powder. Then you compact it. You compact, then you depressurize, then you withdraw. So isostatic pressing, this one is use pressure. Use pressure to press it. Hot pressing is in the industry where you use high temperature to cure the things. Okay, these are the instruments normally in the industry. Slip casting, this one is in the traditional instrument for vase, right? So there is a mold, then they pour in, and then they will flip the mold, dry out, they'll get some thickness, then they remove the die and they get a shape. Okay, this one you read lah, is basically the same thing that I explained just now. This one is forming. This one is casting. Same lah. So you can see from the left until the bottom. You pour, let it dry. You remove the sand, remove the extra cast material. Then you heat it up. Then you remove. Extrusion is like you're pressing some liquid. So for engineering student, you learn about how to do extrusion by all these they call it's called what, a screw mechanism, right? Okay. Then dyeing, binding, and so on, sintering. and so on. Okay, sintering in ceramic is important, where the two silica material, they'll try to bond together. It's like a glass, they'll bond together. Okay, so under microscope, you'll see that there are some bubble joined together when they do sintering. Vitrification is where the glass phase liquefies. So here you see some liquid, then when it become harder, it become crystallized. It can either be this form or this form. So I'll show you the video.
Gaia 4S.
But
After more than a century
this
of
is a 9
experience,
minutes video.
Gaia 4S has
It's quite a long video, so I
160,000
think we
square
skip this
meters
one.
of facilities
You view this
adapted to
video
operate with the
in your
latest
revision time,
generation of top-notch technology.
Okay, so it's a very long video, 9 minutes. 9 minutes, quite long.
Gaia
So
4S.
we don't want to sit here watch 9 minutes video. Okay, so this is another table. They will tell you the material properties, compressive strength, right? Ceramic material table, you won't see tensile strength. They are not good when you pull. Ceramic is not good when you pull, but ceramic are good when you compact it. Yes. Is prepared because it's hot when you cramp, and also is when you compact, it is still there. It's not able to when you pull it, it will break. So ceramic, they are not good in tensile, but they are good in compression. That is the things. So when you read the graph, the table for ceramic, don't go and find tensile. Okay, they are not good in tensile, but they are good in compressive. Tensile strength they still have, but very weak. You see, tensile 200, but the compressive is, I think, 10 times of the tensile strength. Fractural strength also, fracture strength, toughness. So this is a factor that affecting strength of ceramic material. So these are the things. This one you read. Right. So you want to, this one is more on the material science, or if you are fabricating raw material for ceramic, then these are the things you want to avoid in your process. Surface crack. This one is, if your heat treatment is not very good, then there's a crack. Void, inclusion, and large gain. So for this one, surface crack, that's why some of the brake pad, they make it smooth. So they try to avoid any crack on the or scratch on the surface. Right. Okay, so these are the illustration for ceramic. What I mean by inclusion, unjoined poles, how the crack, reaction of the crack, and so on. Pores is just a hole. Pores is just a hole. So pores are also decreased with cross-section area over the load applied, and it lower the stress material at the support. So this one is a volume fraction pores, and y-axis is the strength, transverse strength. Okay. Another type of ceramic called polycrystalline ceramic means you have loss of shape of crystalline cell. Then they are affected by chemical composition, microstructure, surface condition, temperature also. Okay, I want to go to more important things. So this one is ceramic materials. Because they are covalent ionic bonding, so they are low toughness. So we use toughness test to determine their fracture toughness. We use where you have A and there's a jig here. There's a jig here. So for fracture toughness equation, same, you learned in the previous chapter, KIC equal to Y fracture stress square root pi A. This one for ceramic. For steel also same. Okay, so this is application of this equation only, right? So so if you given this kind of question, so if you're given ceramic, then you ask about the strength, then basically only this equation you need to use lah. KIC equal to Y field stress square root pi A. A is the hole size or crack size. So given the fracture toughness 3.6 megapascal square root meter, what is the largest size internal crack, which is A? Right, the material can support without fracturing. Use Y equal to 1 as a fracture toughness. So you want to find A. This one is given. This one given. What else is missing? KIC fracture toughness is this one. Strength is this one. Y is this one. So only one unknown. You rearrange, you get the A. Put in the unit of meter. Okay. You substitute, put in the unit of meter. So A is, what is A? A is the size of the crack. Okay. So got two type. One is edge crack and internal crack. Internal crack is 2A. Remember, when you use KIC equation, the A here is half of the internal crack. Okay. Here, this one, I just put a note there. If the question asks you internal crack, remember multiply 2. Okay, so the next one is just to introduce you a new type of ceramic. For example, the one that you see on the screen here, artificial tooth. So this one is a PS jack, right? PS jack. This one you read lah. So at least you know lah, when your grandmother, grandfather, they go for dentist. At least you know lah. At least you can show off. I know that this one is artificial things. I learned about this one. This is a advanced ceramic. Okay, so you read lah. So important is this graph. This one you familiar lah. So we already covered this morning. So so this one is the temperature. This one is the this one only one. MOG mole percent. This is mole percent. Not weight percent. The earlier one is WT. This one is mole. Mole is mole. Mole percent. Okay. There's another one is AT. AT is atomic weight percent. Go and find either chapter 2 or chapter 3. Forget it. So this one, again, liquid, then it become liquid, then solid is here. Solid is here. So this is also solid. Solid solution, cubic, then MgO, and so on. So in the test, if you see something like this, you just copy. If you really don't know what is this, you just copy. But at least you know where is it. For example, the question asks you this one 1400, this point. You know that this one is on the this one is high hyper eutectoid. So this one, so hypo is beside left hand side of the V. Yeah. Okay. Okay. Something like that lah. Okay. So the question is why is impossible to fabricate something from a pure zirconia? Okay. The transformation, if you see, the transformation of the zirconia ZRO from a tetragonal to monolithic structure is martensic and cannot be suppressed by rapid cooling. Transformation of zirconia. Tetragonal to monolithic. So you can see here, from 1500, this is tetragonal. Then it go into this tetragonal SS plus MgO. And to get monolithic, to get to here, you cannot jump straight from here to here. This graph is normal cooling. Normal cooling. Okay, so there are some cheating step here. You can do it by add some oxide, CaO, MgO, so that the cubic form of zirconia is stabilized. Okay. That's why you see MgO here. It's just to stabilize the zirconia. Okay. So the reason of this MgO percentage here, mole percentage, is to stabilize the crystal structure. Okay. Okay, the rest you read. The rest you read. Okay, so I want to highlight something is that when you tear ceramic, you see the load is this direction, but the crack direction is perpendicular to the crack. The crack is going this way, but the stress is going this way. If it's from here, they are quite good in compressor. If it's from side, from here, then it will crack here. It will crack here. Okay, this one you read. This is just a reference for you. Okay. Now, I go into imperfection, right? Imperfection for ceramic. So they have three types of imperfection or defect. So the first type is atomic defect. So you have three. One is anion vacancy, the negative charge missing, or positive charge missing, or cation vacancy, or cation interstitial. So they are too much or too many these positive charge. Okay, so there are three. So this is the diagram that you can draw in test. So you haven't been asked what is the defect yet. So this is part of the defect lah. So there are two chapters that deal with defect. One is the earlier one in metal, and one is in ceramic. There are two chapters linked with defect one. So don't confuse between the metal and ceramic. Okay. Then another one got two. Also got two, Frankel defect and also Skokie defect. So Frankel defect, you have a loss of blue color. Skokie, you have less blue color. So the rest you read. So you see type involve cation vacancy and cation interstitial pair is called Frankel defect. How they form is when a cation leaving its normal position and moving into interstitial site. Okay, like this one. So they move out from here and then they forget where they park. They park side to other cation. But there's no change in charges. In this area, there's no change of charges because the charges still same. They only change position. Okay, so this one, electronegativity. What is electronegativity? This one you read when the charge is equal. Frankel defects. Frankel defects, this one. There's an equation. So again, you see this vacancies numbers, vacancy equation that you learned in the metal chapter, apply here also. Frankel defects and exponential minus Q 2kT. Here we use Kelvin. So Q is the formation charges or formation energy, and number of latticite, Boltzmann constant. You have two types of Boltzmann constant. It depends on the value that is given. Okay. So there is a 2 here in the ceramic point defect or Frankel defects in the denominator, because 2 defect, a missing cation and interstitial cation, is associated with each Frankel defect. Don't confuse this one with the metal chapter. Ceramic, this one, Frankel defect to divide by half. You know lah, internet in Inti, not stable. Okay, come back already. Earlier one, you don't have 2. In metal chapter, you don't have 2. So don't confuse this one and okay. This one you can see. So created, how this one created, removing one cation and one anion from the interior of crystal, then placing them both in the external surface. So same, the Skokie defect still, you use the same equation, only the formation energy is different. This one. One is franker, one is Skokie. So don't confuse between the two. Right? Now, usually in tests, we'll give you two numbers. For example, NS that you have one Na plus one Cl, right? Now, water H2O, you have two hydrogen, positive or negative. You break H2O, you get hydrogen and oxygen, right? Oxygen is positive or negative? Negative, right? So this is a stoichiometric formula when there's a balance. That's why I asked you. So usually the front one is positive, the back one is negative. But anyway, the main key is stoichiometry. Stoichiometry means balance of your anion and cation or cation. Ceramic compound, they are non-stoichiometric. Okay. So how that non-stoichiometric can happen when there are two variants exist in one of the anion type. For example, you know that iron oxide, you have two colors.